Hello and welcome. In this lesson, we'll explore the key features of logarithmic functions, and we'll start off with the meaning of the word logarithm, which, by the way, is just another name for exponent. So we can think of the words logarithm and exponent as two synonyms. For example, when we say that 2 to the power of 3 equals 8, it means that the base 2 raised to the power of 3 is 8. Now, another way of reading this same statement is number 3 is the exponent, because it sits in the exponent spot. We must raise the base of 2 in order to obtain the answer, which is 8. For short, we're going to write number 3. Instead of is in mathematics, we use the symbol equals. So we're going to write equals. The exponent, oh, wait a second, I just learned that the exponent and log means the logarithm means the same thing. So I'm going to write logarithm. And since it is a very long word, for short, we just write the first 3 letters of it, log. We must raise the base 2. So for the base, we have reserved a special spot here. So at the bottom of the word log, or should I say at the base, in order to obtain the number 8. So number 8 will stay inside. So I want you to take a closer look at where all these numbers are going and what the meaning of each of them is in a logarithmic expression. So remember that this will always be the base, and it's the easiest one to kind of identify and understand. So the number that goes inside the log is the value of an exponential number. And this number in here that equals the log is actually the exponent. So as you can see in here, we have two statements, 2 to the power of 3 equals 8. And the statement 3 equals a log with base 2 of 8 that describe the relationship between the same set of numbers, so which are the numbers 2, 3, and 8. But one expression is in exponential form and one in logarithmic form. So that makes me think, oh, wait a second, that means that I can convert an exponential expression or statement into a logarithmic statement, and vice versa. We can convert a logarithmic statement into an exponential statement. And sometimes when we solve problems in real life, we really need to do this. That's why we really need to learn it. So guess what? We're going to start practicing together how to convert statements from exponential to logarithmic form first, and then from logarithmic to exponential form. So let's get started. So 5 to the power 4 equals 625. So remember that the key word here is logarithmic form. So we are looking for the log or for the exponent. So our eyes should be on the exponent, which in this case is number 4. So we're going to say 4 is or equals the log, the exponent or the log. We must raise the base of 5 to obtain 625. There we go, done. You can try the next one on your own. So again, logarithmic form means that we are trying to spot first the exponent. So here it is, number 3. So we're going to say 3 is or equals the exponent. Wait a second, I have a new name for it, log. And the base is 3 over 4. So as you can see, the bases in logarithmic expressions can be, or logarithmic terms, can be in decimal form or fractional form. Remember, and we'll discuss this later, they can be negative or 0 or 1. And the number that we put inside the log is 9 over 64. Try the next one on your own. You don't need my explanations here, but always double check. So here's the exponent x. So x equals the exponent, or again, log, base 3 to obtain the number, or to obtain y. And next we have the exponent c, which is the log with base b of a. So let's move on to the next set of questions. I hope you enjoyed working on this. Now, in the next set of questions, we are converting to exponential form. Now, usually when I convert from logarithmic to exponential form, Just like when you write an exponential number, so when you write an exponential number, you start writing the base first, right? So for example, you write the base and then the exponent, and then you write whatever number you have there. So guess what? We follow the same order here as well. It's easier. So we start off with the base, and we know where the base sits, right at the bottom or the base of the word log. So 15 is the base in the first one. And the exponent will be the log, because the log of 225 with base 15 is 2. So that means that this must be the exponent. So that means that we have 15 to the power of 2 equals the number inside the log represents the value of the exponential number. Okay, so if you understood this, continue with the next one on your own. So again, always start with a base. So we have number 7. The exponent is -2. The exponential number value would be 1 over 49. So again, the base is 3. The exponent or the log is p. And the value of the exponential number is 7. So one more time, the base is m. The exponent is m, or the log, right, equals the term inside the log is p, and voila, we're done. Now, next we are going to take a look at the features of the graph of logarithmic functions and transformations. And as you have probably, or might have probably guessed already, the graphs of logarithmic functions are somewhat related to exponential functions, because logarithm, exponent means the same thing. So as a matter of fact, the graphs of logarithmic functions are inverses of exponential functions. So how does that work? First, let's recall that inverse functions are reflections of each other about the line y equals x. So what we're going to do is, we're going to start off with the graph of y equals 2 to the power of x. So y equals 2 to the power of x. This is the x and this is the y-axis. So here is 0, here is 1. We'll have the y-intercept at 1. When x is 1, the y value will be 2. When x is 2, the y value will be 4. When x is 3, the y value would be 9. And I'm going to stop there. And when x equals -1, y will be a half, -2, then a quarter. And you get the idea. We've discussed exponential functions already. And here goes the graph of y equals 2 to the power of x. And I will make sure to draw the horizontal asymptote. I'm going to do it with I'm going to draw it with a dotted line. So there is the horizontal asymptote, which is at y equals 0. Now, the next thing that we want to do is reflect this graph on the line y equals x. So where is the line y equals x? Well, the line y equals x must pass through all the points where x and y are equal, which means that x equals 1, y equals 1, x equals 2, y equals 2. I'm just kidding. I know that you know how to do this, but it's kind of fun sometimes. Here we go. I will connect all these points. Here we go. Beautiful. Here we are. And I will also label this reflection line by its equation, y equals x. And now I will inverse this graph. Now, what does it mean to inverse? So in case you have forgotten, I know it's been quite some time, we haven't reviewed this. So to inverse means to switch the x coordinates with y coordinates, or we say switch x with y. So this will form new points. So what does that mean? So let's take a closer look at the graph here. So you see this point in here has the coordinates x is 0, y is 1. So 0 and 1 when switched, 0 and 1 when switched will become 1 and 0. So this point will come right here, 1 and 0. Now, next we have this point, which is at x equals 1, y equals 2. So x equals 1, y equals 2 will become x equals 2, y equals 1. Here is x equals 2, here is y equals 1, here is the point. So next we have this point, the third one. Here we have x equals 2, y equals 4. I'll write the coordinates. So this will switch around to become 4 and 2. That means that we're going to go at x equals 4, y equals 2, so we're landing right here. And lastly, we have x equals 3, y equals 9. So when you switch 3 and 9, we are landing at 9 and 3, so that would be 5 here, 6, 7, 8, 9. So 9 and 3 will be right here. Now, next we have this point in here. So I leave these points for last because they're kind of, tiny and you really feel guilty rounding them somehow. So here we go. -1, sorry, wrong color, -1 and 1/2. So that means that now x will be 1 over 2 and y will be, here's x1 over 2, y will be -1, so that point will go right here. So next we have this tiny little point, x equals -2, y is 1/4. So we're going to say that will produce, or that will change to 1/4 and -2. So right here. And as you can see in here, the graph is getting closer to the y-axis. Guess what? For the inverse, the graph should get closer to the x-axis. And this makes total sense, right? Perfect sense. All right, so we're going to go all the way down. So, and this makes perfect sense, we said, because when we inverse a relation, x and y will switch. So if the horizontal asymptote was at y equals 0 for the exponential function, right? Now for the inverse of it, the asymptote will be not at y equals 0, but at x equals 0, because x and y will switch. And here we go. I'm going to draw the asymptote right here. Okay, so we're going to say there is a vertical asymptote at x equals 0. Now, in an exponential function, we have a y-intercept at 1. Here we have an x-intercept at 1. Why? They're inverses of each other. Now, let's go back to the idea of why were we graphing the inverse anyways? So we were trying to graph the inverse of the exponential function, all right? Just to get an idea what it's going to look like, all right? And now we are going to give it a name, or we have to give this graph, so we have to give it an algebraic name. So how do we determine that? So how do we find the equation of the inverse of y equals 2 to the power of x? There are 3 very simple steps actually that we have, or we follow, when we are converting or finding the inverse of a function. So first we make sure that if we have f of x in here, we replace it with a y. And then we switch x with y. And when we switch x with y, so from y equals 2 to the power of x, if they switch places, then it will become x equals 2 to the power of y. So next, what we want to do is express this exponential expression, into logarithmic expression. So you're going to say y is or equals the exponent, or should we say log, with base of 2 in order to obtain the term x. So what we are saying in here is that by inversing the graph of y equals 2 to the power of x, which means by switching x with y, we actually created a beautiful equation for this graph, for the green one. So y equals log with base 2 of x would be one of the many parent functions of the logarithmic function. We use this as a reference, just like we use y equals 2 to the power of x for exponential functions. Now what we are going to do is compare the two graphs. So we are comparing y equals 2 to the x with y equals log with base 2 of x. Now we're going to start off with the exponential. So for y equals 2 to the power of x, what's the domain? Well, we say that the domain in exponentials is any real number. And for the range, we say is any real number, and that's because it's a solid graph, right? We see a solid line in here, so we have to state XCR, such that y is bigger than 0 because the graph is located above the horizontal asymptote. Now, exponential function has no x-intercept, but it has a y-intercept exactly at 1. And it has one asymptote, which is horizontal, and its equation is y equals 0. Now, when you look at the graph of the inverse of exponential or logarithmic function, we're going to say that the domain of it is restricted by the vertical asymptote. So the domain will be all the x values bigger than 0. So we're going to say any real number x under the condition that x is above 0. For the range, look at the range. Here are the y values, negatives, positives, and 0. And it seems that we have graph in the negatives. We have graph here at 0, y equals 0, and we have graph above 0, which means that y is basically any real number. Now, x-intercept, yes, we got 1. The x-intercept is right at 1. And the y-intercept, we have none. So we have an x-intercept at 1. We have no y-intercept. And we have a vertical asymptote, which is exactly at x equals 0 because it's on the y-axis. As you can see, these two inverses have kind of inverse features as well. So here we have XCR, YR. X bigger than 0, y bigger than 0. No x-intercept, no y-intercept. Y-intercept 1, x-intercept 1. Horizontal asymptote and vertical asymptote. Now, the next thing that we want to take a look at is the transformations of logarithmic functions, and for this we'll continue with the second part of this video. Thank you for watching, and I hope you find these instructions useful. Bye for now.